welcome to our very last lesson. This is lesson 10C, which is inference, hypothesis tests, and confidence intervals for linear regression slope. So let's get started. So let's first talk about what we mean by linear regression slope. Essentially, what we are testing for is, do we have evidence of a linear association between two numerical variables? So let's talk about what would a scatter plot look like if there was no association between the two variables. So no association would likely give us a scatter plot maybe like this, where the points are completely all over the place. I can't really see any kind of pattern, let alone a linear one. And if I were to calculate and draw a line of best fit of this set of points, that line of best fit would look something like this. There's no association. The slope of that regression line is going to be approximately 0 because the points don't really lead in a specific direction or pattern. Right? On the other hand, if there is an association between the two numerical variables, specifically a linear association, then the points are going to look maybe like that, or perhaps like that, where we can see a clear pattern. In this case, on the left, the line or the points are going up, so I see somewhat of a positive linear association. With the points on the right, you can see them going down, so a negative linear association. And when I draw a line of best fit through those points, right, that line does have a slope that is not 0, right? It's either a positive number or it's a negative number, but it's not 0. So when we do a test, that is kind of what we're looking at. What about this graph though? Right? Is there an association? Right. Well, I do see a pattern, but that pattern is not super defined, and the points are pretty far spread apart from each other. So even though I do see a pattern, a slight positive pattern, the points are definitely not as clearly defined one way or the other. So at what point, at what level do we say there's a numerical association, and when do we say there's not? All right, we have the words weak and moderate and strong, but there is a way to actually test where we draw that line. So where do we draw the line between yes and no, right? That's what our linear regression t-test is testing for. And a linear regression t-interval is testing for the actual slope. It's an estimate for what the slope of that line of best fit could be. So is there evidence of a linear association between blah and blah, where the blah and blah are both numerical variables? That is the question we're asking with this type of test. So let's talk about assumptions and conditions real quick. We're not going to spend a lot of time on this not because they're easy, but because they tend to be really complicated and involve information that we don't always have or can't get very easily. So just to go through them really quickly, obviously we want to check for, is our sample of data random or representative? Does the data appear to be linear? If it doesn't appear to be linear in real life, we would not actually do a linear regression test or interval because that would be a waste of our time. So we're looking, we do want to see, does the data appear to be linear? Does the plot thicken, right? And the plot should not thicken. If we see something like this, where maybe it starts off fairly linear and close to each other, maybe strong, and then as the points go on, we see spreading out of those points, that's not a good sign. That would tell us that a linear model is probably not the most appropriate model for this data, or that we should kind of split it up by X value. So we don't want to see that. And then we need to check a normality condition. And what we're checking on linear regression data is the histogram, or the graph of the residuals, should be roughly normal and without outliers. So if I were to take each residual and plot them like this, that's what I would want to see. Right? Degrees of freedom for a regression test, and this is important to know later, is n-2. So we're taking away, it's n-1, but then because we have an extra variable that we're dealing with, there's 2 numerical variables, we take off another 1. So it's n-2. Ideally, the normal condition or normality condition would look something like this, where for each value of x, the residuals for that value form something that is roughly normal or without outliers. But again, that gets really, really complicated. So generally, when a question like this shows up on an AP test, they tell you that conditions are assumed to be true, or They've already been checked and verified, don't worry about it. At the very least, they would give you a histogram or a graph of the residuals so you can say like, hey, they're normal. But we very rarely see questions like this on an AP exam where you have to talk about conditions. So I don't want you to worry too much about conditions, which is why I just kind of very quickly sped through them. So let's actually do a test or interval. So formula-wise and step-wise. So the first step is to define our parameter. The parameter we are dealing with on a linear regression t-test t-interval is the slope. The slope of the line is our parameter. So beta 1, so it's uppercase, kind of a fancy looking B, is the true population slope of the linear regression line between x and y. And the way we can define that in words is it's the true mean change in y for each 1 unit change or increase in x. Okay? So that would be our parameter. For a linear regression t-test, our hypothesis statements, the null is that beta 1 equals 0, basically saying that there's no linear association between the two variables, that the slope of that regression line would be 0. And then our alternate is that beta 1 is not equal to 0. Right? So again, null is that there's no linear association. Alternate is that there is a linear association. Notice that I just put not equal to, right? In the scope of this class and what we're dealing with, we don't even really go farther than that. We don't really say greater or less. We really are just testing for, is there some kind of linear association, be it negative or positive? When we talk about our actual test, right, we'll have to find a formula for a t-score, and then we'll use that t-score to find a p-value. I'll show you in a minute, but the information we're given usually does all of that work for us. But just to go through the calculations, right, formula for a t-score or a z-score is we take our observed value, our sample statistic, which would be the slope from the sample, minus our null hypothesis value of the slope, which is 0, so minus 0, divided by the standard error of the slope, which is also a value we would be given. So it's always statistic minus parameter divided by some kind of standard deviation of the statistic. And pretty much all of these values are given to us. For an interval, right, our formula, basic formula is statistic plus minus a critical value times a standard error. So what that looks like for this type of problem, again, our statistic is the slope from the sample. Okay. Critical value would be a t-star, but remember our degrees of freedom for a linear regression problem is n minus 2 because we have 2 numerical variables that we're dealing with. And then times, again, that standard deviation or standard error of the statistics. Again, this would be given to you. So let's jump into an example. So on this question, we have our data right here. And the question is basically saying, I didn't put in the intro to this, but students took a CTBS, which is some kind of like test for understanding, whatever, and there's math score and a reading score. And we're looking for, is there a linear association, or do we have evidence of a linear association for all students who would take this test between math and reading scores? So is there evidence of an association? We're going to test an appropriate hypothesis and state our conclusion. And then it says, assume all conditions for inference have been met, which means we do not have to check conditions. We do still need to define our parameter and write our hypothesis statements. And we also need to do the calculations and write a conclusion. So let's start with our, that's the name of the test, t-test for linear regression slope. You could also call it a linear regression t-test, something like that. So our parameter is first, right? So beta 1. Right? You could also just define it as beta, but uppercase fancy looking B. True mean change in y, which is going to be our reading score for each 1 unit change or increase in math score. Okay, just as a recap from when we did the review, when I'm looking at my data up here, the reason I know that the y variable is reading and the x variable is math. So firstly, we were told up at the top, dependent variable is reading, dependent is the y. But remember also in this table of data, okay, Whatever word you see that represents a variable, in this case I see the word math, that is your x variable, always. So we can know from those two things. So x is math, y is reading. So when I define my parameter, I'm saying the true mean change in y, which is the reading score, for each 1 unit, 1 point increase in x, which is math score. So we're defining, this is basically saying this is the true mean slope of a linear regression line where x is math score and y is reading score. So then our null hypothesis is that beta 1, that true mean slope, is equal to 0, meaning that there is no linear association between math and reading score. Our alternate is that beta 1 is not equal to 0, that there is a linear association between math and reading score. When you're writing your hypothesis statements, it is totally fine to just null as there is no, you don't have to necessarily say the beta 1 equals 0 part, but it will come in handy usually on multiple choice questions or just generally understanding what we're testing for is that there's a slope. Okay. But when you're writing your hypothesis statements, it would be acceptable to just say null is that there's no linear association between math and reading score. Make sure to put context. An alternate is that there is a linear association. Linear is important, right? We're testing specifically for a linear association, not just for a general association. Okay. So next we would do our calculations. So to get all the numbers we need for those calculations, I'm looking at the row in the table that starts with our x variable, right? That is the slope row, is what I like to call it. And because that is what we are testing for, is a slope, that is the row that I need. I don't need anything else in this entire problem. I only need the slope row. So this first number under coefficient, that is the slope actually from our sample data. So the slope from our sample is 0.8658. The next number over is the standard error of the slope. Notice that it says SE of coefficient. So it's the standard error of our sample data for slope. So let's look at our formula. Right, our formula was, I don't have it on the screen, but it was the slope, 0.8658, the slope of the sample, minus 0, because 0 was our parameter, our null hypothesis slope, divided by our standard error of slope, which is 0.1045. And if I were to calculate that, right, if I were to say, okay, 0.8658 minus 0, I guess I didn't really need to type that part, divided by 0.1045, that would give me my t-score, which is 8.285, etc. Right? But notice that on my little table, the next column over says t-ratio, 8.29. That's pretty much what I just got on my calculator. So they do actually give you the t-score in that table. And then the next column that says probability, you can probably guess, right? That is our p-value. So while I could take that t-score and use a t-table to estimate a p-value, the table of information that we're given is typically pretty much always going to also give you the p-value. So our t-score is 8.29, our p-value just says less than 0.0001, so it's very small. When you are writing this out on a free response question, right, it's okay to not put the formula as long as you write the name of the test, so t-test for linear regression slope. The formula for this isn't too bad, it's basically just 0.8658 divided by 0.1045, but you don't have to write it as long as you name the test. You should be naming the test anyway, to be honest, and then write your p-value. Right. Degrees of freedom would be sample size minus 2. I didn't give you the pre-information here. The sample size was 20. There were 20 students. This particular set of data actually also tells us the degrees of freedom, but that's not usually something we're given. This little extra kind of table up here is not usually given to us. So n minus 2, there were 20 students in this sample, so 18 is our degrees of freedom. And then from there, we write a conclusion. Right, so same way we've always written a conclusion. If p is small, reject the null. If we're rejecting the null, we have evidence of the alternate, and vice versa. So if alpha is 0.05, because they didn't give us one, our p-value of less than 0.0001 is definitely less than 0.05. We reject the null. which means that we have evidence. There is evidence of our alternate hypothesis, that there is a linear association between math and reading score on the CTBS. Now, you could also say there is evidence that the slope, true mean change in reading score for each 1 unit increase in math score, is not 0. That would also be appropriate. So that is our linear regression t-test, right? They give us pretty much all of the information we need to do this quickly. So most of what you're doing is the writing part, kind of setting things up, thinking about your hypothesis statements, and then using that to write a conclusion like this. So let's move into our confidence interval. So same data, I didn't change that up. We're just going to now do a confidence interval. Like I said before, a confidence interval for this type of problem is basically going to estimate what is that mean slope. What is the slope of the regression line for all people who take this test in terms of that linear relationship between math and reading score? So part A, the test basically told us we do have evidence that the slope is not 0, that there is a linear relationship. A confidence interval is going to give us a little bit more specificness. So again, if this were a problem all by itself for your response, I would define the parameter, I would name the test, right? So the test, this is a t-interval for regression slope or a linear regression t-interval, however you want to write that. We have the same parameter as before, the true mean change in reading score for each 1 point increase in math score. But now we get to the actual calculations. We're still not doing conditions because they told us before conditions were checked. The calculations part is a little bit trickier, not a whole lot trickier, but the information we're given does not give us an interval. So we do actually have to do the math on our own. So remember, our formula is statistic plus minus critical value times standard error. So we're given the statistic. Remember, that's our sample slope, so the 0.8658. We are given the standard error, 0.1045, but we do need to find a critical value. So if I know my degrees of freedom is 18, and minus 2, there were 20 students in this sample, minus 2 is 18. I would then go to my t-table, so not chi-square table. I know we've mostly been using the chi-square table in this particular unit, but we are talking about t-table because this is a t interval. I would go to my t-table, look at the degrees of freedom for 18, and we look up the critical value for 90%, which comes out to 1.734. If you need a quick reminder of how to look that up on the t-table, make sure you let me know. I don't have it open right now, or else I would go through that real quick. So when I do my confidence interval, I start with my statistic. So that was the slope from the sample, 0.8658, plus minus my critical value, 1.734, that I got from the t-table, times my standard error of the slope, which they told me was 0.1045. Then I go into my calculator, right, and I do that math. And yes, I do actually have to sit here and do the math. There's no shortcut. So I'm just doing the math. I have to know the formula a little bit. I forgot the what did I do? 4, 5. Here we go. Right, so that gives me the lower end of my interval, and then I do the same thing with a plus right there, and that gives me the upper end of my interval. So I'm actually using the formula to get the interval. And then when I interpret it, remember that the parameter I'm interpreting is the slope, the true mean change in reading score for each 1 point increase in math score. So in other words, we're saying that as math score increases by 1 point, right, the average reading score is going to change or increase by between 0.685 and 1.047 points. So we're estimating what that slope is. Okay? So we're 90% confident that for each 1 point increase in math score, right, the reading score for a student will increase by between 0.685 and 1.047 points on average, right? We want to make sure we're including the word average or mean, so we could also say the mean reading score for a student will increase. We could put the on average somewhere else in the sentence, but we do need to make sure and mention that it is an average and not necessarily like an actual prediction for each individual student. It's an average prediction, right? So that is how we do our confidence interval. Right? And that's pretty much it for this lesson. So it goes by a little quicker because we're not usually checking conditions. It also goes by quicker because we are given most of what we need. We do have to actually use the formula for confidence interval. Some of you may look on your own. When you go to stat tests towards the bottom, there are ln-reg t-test and ln-reg t-intervals, but that would be if you were given numerical data that you had already put in stat edit. You put like your x's in L1 and your y's in L2, then you could use ln-reg t-test or ln-reg t-interval to calculate or to do that test or to do that interval. That is not typically how we are given information like this on the AP exam, which is why we do it the way that we do it. But in case you are curious, if you're doing your own testing and your own stuff, if you have actual data, you can do your interval and test that way in the calculator. It's just not how we do it. So that is the end of this lesson. That's it, y'all. We're done with lessons for the year.